record. All right, so if we take a look what we wanted to accomplish today, I kind of got that accomplished yesterday. We talked about the heat of fusion, heat of vaporization, and we did actually the one multi-step problem. A lot of these have the answers to them, so we'll take a look at another one, and then as it says, there's no test on Monday, obviously, 3-day weekend. Not gonna mess with you on that. So let's take a look at a few of these. As we did this one here yesterday, this takes you through the whole gauntlet. So hopefully you can see all of that. Let's just pick one. So we'll take a look, we got 6 here. Looks like we'll do number 6. All right, so what is the final temperature when 0.850 kilojoules is added to 10 grams of ice? So we have 10 grams of ice. We need to turn that to water. Because it's at 0 degrees. And then we want to figure out what type of change of temperature we can get. The first thing we need to do is make sure that 0.850 kilojoules can melt 10 grams of ice. So if we take a look, 10 grams of ice. Heat of fusion, every 1 gram of ice requires 333 joules. 10 times 333.
It's 3,330.
So if we take a look there, if we can do the conversion in our head, that would be 3.3 kilojoules. So this 0.850 kilojoules is not enough heat to even melt that. So we don't have to worry about these parts. That's not going above 0 degrees because you won't be able to melt all the ice. And keep in mind that whenever we're looking at a problem like that, we're not sitting there, we're assuming that the system is constantly mixing. We're not sitting there, well, all the ice is on top, you know, we're not dealing with that. We're assuming that it's constantly mixing. So that one quite simple. Is there any problems that were tried by you either on page 10, 8, 9, or if you tried some on 13, 14, and 15? Is there any that you want me to go over? Let's get that out of the way first. No. No, then let's see. Is this stuff here? Are we over this? Do we get this? I mean, we can move on to enthalpies of formation or reactions, or would you guys like for me to try a few more problems? I've got the chat on. If you don't want to speak out loud, you can send me a private message on that.
Can we just like try one more problem?
Yep. Any in particular? All right. So let's take a look here. Heat of fusion of mercury is this. Calculate the quantity of energy transferred when 4.37 moles of mercury freezes at a temperature of negative 39 degrees. So that one, they give you moles. It's highlighted. Keep in mind that it wouldn't be highlighted in another situation. So if we take a look, 4.37 moles. if our heat of fusion is in grams, we need to change from moles of mercury to grams of mercury. Periodic table, every 1 mole of mercury is 200.59 grams. And every 1 gram is 11.4 joules. So 4.37 times 200.59 times 11.4 gives us, what do we got? 3 significant digits. So I didn't get 10.3 kilojoules. I'm not sure if they used something different from the periodic table, but that comes out to 9,993 with 3 significant digits. We would get 9.99 kilojoules. Unless I switched some numbers in there in my calculator. So I mean, a lot of times you could be given something in moles, or this could be a molar heat of fusion, which instead of being in grams would be joules per mole. 55, and what is the temperature of both the iron and this one will be good to practice on your own because you're trying to find the final temperature. A 237 gram piece of what is the specific heat canceling? Let's do one like this real quick. So we have a 237 gram piece initially at 100 degrees Celsius. So basically they put it in, boiling water. When the system comes to thermal equilibrium, we get a temperature of 15.3. What is the specific heat capacity of the molybdenum? So if we take a look, we know that Q equals negative Q. Now with this one, it's kind of cool because we can actually solve one whole side of this for Q and then set it equal to the other side of the equation versus having the big one like we did yesterday when we were searching for the final temperature. We can take this water and we can find that Q. So the Q for the water, it is gaining the energy. So if we take a look, we've got 244 grams of water. The specific heat capacity of water is 4.184 joules per grams degrees Celsius. And we've got a change of 5.3 degrees Celsius. The water went from 10 to 15.3. So that is 5.3 because you take final minus initial. So .184 times 5.3. We get 5,410.7 grams cancel out, degrees Celsius cancel out. We end up with joules. I think it was Leah that said on a problem like this, and maybe I confused the question, but if you take both of these because you are just finding the energy, we could turn this into the negative. But let me show you the difference with that. We could also take the absolute value of both of these because the energy gained has to be equal to the energy lost. But here's where that thing comes in. It's when you're dealing with this delta T. because the final temperature of this is 15.3. So 15.3 degrees Celsius minus the initial temperature, which is 100 degrees Celsius. The specific heat capacity of this, we don't know. That's what we're looking for. And the mass of this is 237 grams. So notice for this, we would want to make one of these negative, because when we subtract this, we're going to get a negative number. I get negative 84.7 times S times 237. Let's go ahead and multiply that by 237. We get negative 20,073.9 S equals, maybe this is why they use C a lot, because my S's look like 5s, unfortunately. Negative 5410.7 joules. So if we take a look, if we divide this by that, the negatives will cancel out. Negative 5410.7 divided by, and we get S being 20,073.9. We get S being 0.2695. Subtraction here is actually 5.3 with that subtraction gives us 2 significant digits. So that would equal 0.27. And we have the joules per grams degrees Celsius from right here. So the degrees Celsius is going to stay because we're just subtracting it, and we have that grams right here. So when we divide this, we would still have grams degrees Celsius here. I think that if obviously we could have just made this absolute value on that, and I think that was what Lily was asking about. The only time that you really need to, I mean, you can obviously do this. This is always going to get you the right answer if you keep track of that. But unless you're solving for the actual final temperature, like in a problem like this, then you can solve one side and then solve the other side. And if you keep that in mind, straight in your head, the amount of heat gained must be equal to the amount of heat lost. You know the molybdenum is losing energy because it's going down in temperature, and that the water is increasing in energy. If we go back to this, one of the cool things here is we had that water and water. If we were to put that formula together, we would get the mass of each water times the specific heat capacity of water times the change in temperature of one. Let's just say this is the 100-degree water. And that being equal, the amount of heat this lost equaling the amount of heat that the other water gained. Since we used 50 grams of each, that 50 grams would cancel out. The specific heat capacity of water would basically cancel out as well. And that then we would just be basically getting our delta T. And we would think that 100 to 0, that would put us somewhere around the 50 mark. The metal, if we look at this equation, let's say that this is for the water. Then we have an issue. We tried to use the same mass of the metal as the water. So those would cancel out. But the big issue would be the specific heat capacity of the metal versus the specific heat capacity of the water. And we also have one going from 100 and one going from 0. So we do have a change in temperature there. And then the water here and the ice here. Well, the problem is, again, we have this formula, but then we also have this plus, if we put this as the ice and this is the water, plus that melting. And so this is why each of these are going to have an actual different temperature when we do that. This one should be right at the halfway point. This one should be some type of ratio of the specific heat capacity of water versus the metal being 0.9. And this one, we have to take into the effect of the water, the ice melting by absorbing energy from the water that's added. Questions? So if we take a look, we'll just do a little bit here. I don't want to get carried away. But if we take a look, we're dealing with standard enthalpies of formation, and there are different types of enthalpies, but one major difference with this is that the standard conditions are not the standard temperature and pressure. Pressure is the same, but temperature is room temperature. And basically what they're saying is like what you would have in a laboratory or something like that. Now the reason for that is that on the periodic table, all of these states of matter are based on those standard conditions. And elements are considered to be in their ground state, and that's the physical state in which it exists at standard conditions. To show those standard conditions, usually we put a null, a superscripted null up at the top. And we'll get these on Monday, but I just wanted to show you that we've already covered certain special types of these. Obviously, you can sit here and say, okay, molar combustion. That's the amount of heat released when you combust, since it's molar, 1 mole of a substance, right? If we take a look here, molar enthalpy of vaporization. So that is the amount of energy when we vaporize 1 mole of a substance. So we've got that for water, and it was 2,260 joules per gram. How could we figure out how many joules per mole this is? Well, if this is 1 gram down here, and we want to convert this to moles, we need to put every 1 gram up top, every 18.01 grams is 1 mole on bottom. 2,260 times 18.01. And we get 40,070, 102 joules per mole. Usually this will be shown to you as 4.1 kilojoules per mole. Molar enthalpy of fusion, again, it's the molar. So if we were to do the same thing, fusion, remember, is the melting. So if we take 1 mole of water and change it into 1 liter, we can do the same exact thing dealing with our 333 joules per gram, change the grams to moles, and then we could have the molar enthalpy or molar heat of fusion. Cool. I think we'll start on Monday with these. Question came up, do we have any specific homework that you want us to do? Basically, make sure that you can do some of these problems. The answers are there. Pick ones that you read and you sit there and say, oh, that sounds hard, and then try to go through it. But all of these problems were done in X chemistry, and I think at this point, all of you guys have taken X chemistry, so this will just be a review for you to get you up and running. And then looking at the rest of the unit for next week, we got the heat of formation, if you recall that. Products minus reactants. Hess's law next week. And then bond energy. And keep in mind when we look at this, this is the only one that is kind of really different. You take the summation of the bonds broken minus the summation of the bonds formed. And a lot of people have trouble with this aspect when it comes to bond energy, because a lot of times if you're in biology, they tell you that energy is stored in bonds. Well, chemistry shows us that, you can't just release this energy. It's not like it's stored in there. Usually you have to put energy in to break the bonds. And then when the bonds are reformed, hopefully the bonds are of lower energy. So energy would be given off in the case of an exothermic reaction. That goes to, I think, if you recall this guy right here. If we take a look at this, this is closer together, right? And this is that energy, the bond energy diagram based on atomic distance. So if we take a look, if we try to put atoms that are together and we get too close, basically we're fighting the repulsion forces from their nucleus. So we need to put energy in. Well, if we find this distance right here, if you recall, that is our key point. That is where we have that bond, and that's usually where you have a negative energy, and that's what biologists are talking about whenever they talk about energy being stored in bonds or whatnot. Let's say that we put energy in and we break these up, and new bonds are formed, and instead, let's say that our energy is here for that new bond formed. Well, then that energy right there is the energy that we can actually, retrieve or release by basically taking it to a lower energy state. That's why combustion reactions are a lot of times, well, that's not a combustion reaction. Combustion reactions are a lot of times exothermic because we're making some things that are pretty, stable, carbon dioxide and water. All right, and the last thing for this unit, that's it actually, bond energies. So again, the question was, do you have any specific assignment? Not really. Try a few of these problems. If you have issues with any of them, then we can go over them on Monday. Other than that, enjoy the 3-day weekend. As always, if you are behind on something, contact me, and let's get you back to where you need to be. And that's all I got. You guys can head out of here. If you get 20 minutes, you should at least be able to get one of these if you're not too tired, because on Tuesday, if everything goes the way that they're saying it might go, then that means that we have 7:20 start time, or 7, what was it, 7:10 or 7 o'clock? 7:10 start time. Have a good weekend, guys.
Mr. Jackson.
Yep,
Have a
yep.
good week.
Thank you.